Take steps in freshman enzyme. Jenny, I can tell you right now.
So let me have your attention up here for a minute, please, or more than a minute, about 5 minutes. I'm going to just go over a couple things with you here, and we're going to start the assignment, do a couple of monthly assignment with you. Lesson 7.5, we have a new distribution. It's called the chi-square distribution. So I know CHI doesn't look like chi, but it's pronounced chi. The Greek letter chi looks like a cursive S. So that says chi squared. This letter right here is chi. It's Greek letter chi. Now, the distribution looks a little bit different because all chi-squared values are positive. So the distribution looks like this, and it's usually kind of skewed right. Okay? And you're going to have a chi-squared right, which is going to be on the right side of the distribution. So chi-squared right, instead of a z-score or a t-score, we've got a chi-squared right score. Same thing on the left over here. We've got a chi-squared left score. Alpha represents the area of both tails. Alpha equals total area of both tails. A couple other things we're going to review. Sample size. What variable do we use for sample size? Anybody? N. Standard deviation of a sample. It deals with a sample. We're going to use a Roman letter, which is normally kind of like one of our English letters. What letter do we use for standard deviation of a sample?
S squared.
S, just S. Let's go down here. Let's jump down here. Variance of a sample.
S squared.
S squared. Okay, now we're doing the last two things I have are population measurements. They're parameters. So we use Greek letters for parameters. Standard deviation of a population. Anyone know what that Greek letter is called? It's called sigma, lowercase sigma. Variance of a population would be what? Sigma squared. So what we're going to be trying to do, instead of trying to predict a population mean or a population proportion, we're going to be trying to predict a population variance or a population standard deviation. And let's go ahead and just do number 5 off your assignment as an example. So write this down on your assignment. Number 5 on page, on lesson 7.5. By the way, the rounding rule, talks about the rounding rule on page 380. It's the same rounding rule that you had for the means. What it says is that if you're using raw data that you have to put into your list, then you go out one more decimal place than the data that you put in. If you don't have raw data, then you round to the same number of decimal places that are given in the problem. That's the same rounding rule we used on lessons 7.2 and 7.3. The only rounding rule that's different is proportions. Proportions, which we did yesterday, lesson 7.4, then you always go out 3 decimal places. All right, so anyway, we're on lesson 7.5, number 5. Find the 95% confidence interval for the variance and standard deviation for the time it takes a customer to place a telephone order with a large catalog company. If a sample of 23 telephone orders has a standard deviation of 3.8 minutes, assume the variable is normally distributed. Do you think that the times are relatively consistent? So it says they have a sample of 23 telephone orders. So I put 23 in for which variable? N. Yep. So you're going to have 23 minus 1 on the left fraction in the numerator. Same thing over here. 23 minus 1. And it says the standard deviation of that sample was 3.8 minutes. So I put 3.8 in for which variable?
The S.
S. Yep. 3.8 squared. 3.8. They're not ever going to give you the population standard deviation because that's what we're trying to predict the population variance. Next, we have to go to our chart. Look up chi-squared right and chi-squared left. Well, this is where the confidence interval comes into play. It says, or the confidence level comes into play. 95% confidence. That means there's 0.95 in the middle. So if there's 95% in the middle, what percent would be in the tails? 5% total, right? Our alpha would be 5% then. But then you always have to divide that by 2 to get 0.025 or 2.5% right here. Same thing here, 0.025. Now, if you look at your formula, your chi-squared chart, chi-squared distribution that I just showed you, get that out. And we'll talk about that in a second here. Let's move this so it's on the video. You might not be able to read mine, so look at your copy that I gave you. And you're going to see a whole bunch of numbers across the top for alpha. You're always going to divide by 2 before you look at this number, though. So we took 0.05 divided by 2, and we get 0.025, which is up right there. Okay? So then my degrees of freedom is n minus 1, so I do 23 minus 1, which is 22. So I come down from 0.025, and I come over from 22, and I get 36.781. Everyone see how I got that? Again, take your alpha divided by 2. That's going to give you your chi-squared right number at the top. Come down. On the left, you have degrees of freedom, which is n minus 1. So 23 minus 1 is 22. Come over. 36.781. Now be careful, because your chi-squared right actually goes on the left fraction. 36.78. Now, the chi-squared left is what seems to throw people off. Chi-squared left, people have a tendency to go to the 0.95 column. There's not, 95% of the area is not to the right of chi-squared left. It's 95% plus 2.5%. You've got to add these two numbers together. So what do you get if you add 0.95 and 0.025? 0.975. So you got to go to the 0.975 column. So 0.975 is right there. Again, I come down, come over from 22, 10.982. And our population variance, sigma squared, is going to be somewhere between these two answers. Now, you might want to, on your assignment sheet, you might want to go ahead and just draw lines. Like connect the 0.9 and the 0.1 columns with a line here. Those two columns always go together. If you use the 0.10 column, you'll use the 0.90 column for your chi-squared left. Draw another line connecting 0.95 to 0.05. Draw another line connecting 0.975 to 0.025. Draw another line connecting 0.99 to 0.101. And then finally connect your first column, 0.995, with your last column, 0.005. So those columns kind of work together. All right, next up, we'll type it in the calculator and come up with our answer. So let's do, let's see, 23 minus 1, that's 22 obviously, times 3.8 squared, divided by 36.781. So that's my left number. Now hit second enter. Change that 36.781 to 10.982. So my variance, my population variance, I'm 95% confident that the population variance is going to be between 3.8 was given to the nearest 10th, so I want to round this to the nearest 10th. So I'm going to go 8.6 on the left and 28.9 on the right.
So which number do you want to figure out how to round it?
You look at, right there, 3.8. Look at your standard deviation. Okay. Now, she asked, how do you know what to round to? Which number do you look at? Look at your standard deviation. If that's to the nearest 10th, then this answer will be the nearest 10th. Now, let's also do a confidence interval for the standard deviation. This was a confidence interval for the variance. So what would I have to do to both of these numbers to get this second answer here? Think about what would you do to this to get to this. Square root. So you gotta take the square root. Now don't take the square root of 8.6, take the square root of 8.637. Go out at least 3 decimal places. Otherwise you might be off a little bit. That comes out to 2.93, so you can round it to 2.9. And then square root of 28.927. 5.4. And the last answer I'd like you to label. So whatever the label is on the standard deviation, the sample standard deviation, we'll use the same label on the population standard deviation. So this was 3.8 what? Do you remember? Minutes. So this is going to be 2.9 minutes, 5.4 minutes. So we are 95% confident that the standard deviation of the time you have to wait to make an order is somewhere between 2.9 minutes and 5.4 minutes. So are they very consistent? I would say yes, that's pretty consistent. There are only a couple minute difference here in standard deviation. So I would say that's pretty consistent. Most customers wait about the same amount of time, in other words. You don't have one person that waits 1 minute and another person that waits a half hour. Now, if I was to label the top answer, any guesses what the label would be? It's not just minutes, it'd be something a little bit more than that. You square these numbers to get these numbers, so what do you think this label would be? Minutes squared, which really doesn't make sense. I mean, it doesn't really make sense in our brains probably, so that's the reason I'm not going to make you label the first one. But the second one is minutes, and that does make sense. Does anybody have any other questions about that? All right, I'm going to put 7 up here too, but if you feel like you don't need to watch me,